Okay, so welcome to the next lecture of this course, Fundamentals of Solar Photovoltaics and Technologies. Today is lecture 7. So we will talk about determination of solar radiation with respect to geometrical parameters on a yearly basis. On different basis, basically we'll take different considerations of calculating the solar radiation at a given location in India. Examples will be taken in the Indian context, but those calculations may be valid elsewhere also. So just to recap, what we did in the last few classes was to learn about the time corrections which are needed to account for the local differences in the longitude and latitude with respect to the countrywide single time zone. So we learnt the importance of local standard time meridian, time corrections, local solar time and hour angles. These help us to correct for the time at the local at the given location in a very precise manner. And then we also learnt the geometrical parameters, namely the angles such as declination angle, elevation angle, zenith angle, solar and surface azimuthal angles. These are important in determining the angle between the sunlight or sun ray and the surface normal. And we also learnt about how do we determine the sunrise, sunset and day length. So these together will help us determine the radiation on a given time and day at a given surface at an angle to the horizontal or the surface. The detailed information about these topics you can read in chapter 3 solar energy of the book Solar Energy Principles of Thermal Collection and Storage by S.P. Sukhatme and J.K. Nayak. It has a very lucid description of all the things that we have done in last couple of classes and also this class. So let's first take a problem. How do we determine sunrise and sunset for a given location? So let's say we assume a date of June 21 and location is Mumbai with the given longitudes and latitudes, and we assume that the surface is horizontal is facing south, which means gamma is equal to 0, and the surface is inclined with respect to horizontal by an angle of 10 degrees. So for June 21, we know that n is equal to 172. You can just count from January 1, and using the equation of time which is given on the right, we can calculate what is EOT in minutes. So that is minus 1.44 minutes as we plug in the values here. So this is minus 1.44 minutes. Then using this value of n, we can also calculate what is the value of declination angle, that is delta, and delta for June 21 turns out to be 23.45 degrees. And omega s value can again be calculated, which is cos inverse minus of tan 19.12 degree minus 10 degree, that is beta. So this is basically, you can say it's phi minus beta, and what we have here is delta, and omega s turns out to be plus or minus of 94 degrees. So omega s will help you in calculating the value of day length. So time correction we can work out as 4 into lambda minus LSTM plus equation of time, and this gives us a factor of minus 31.84 minutes, again in minutes. So sunset can be worked out as 12 minus 1 over 15 cos inverse minus of 19.12 minus of, so there should be a difference of 10 degree here. So 19.12 degree minus of 10 degree, because it is phi minus beta, and again here 19.12 degrees minus 10 degrees. So this we can cross out, phi minus beta. Okay. So from this you can determine so this value will be, I think, about 5.20 hours, and this will be another value 17.8 XX hours. So, these are the corrections. I should have made these corrections in the slides, but nevertheless we can cross these out. So, these will be the values of sunset and sunrise that will be obtained by putting in the values of the time correction and the value of phi and beta in these equations. So, this is how you calculate basically using the longitude, latitude and the day number. First you calculate the equation of time, then you determine the declination angle, then we determine the hour angle, and from these we can determine what the sunrise and sunset. I am sorry, this should be sunrise. So, this is how you do the calculation, just a way to calculate sunrise and sunset, and the difference between the two can tell you what is the day length. So, you can do the homework and do the same problem for December 21, and that should tell you that how the day length changes and how the sunrise and sunset changes for a December 21 day, which is the shortest day, and this June 21 on the other hand is the longest day. So, now let us talk about solar radiation measurements. How are these measurements made on a given location at a given time and in different contexts. A lot of this discussion is taken from the book Solar Energy by Sukhatme and Nayak. So, I would strongly recommend you to read that chapter, chapter 3. So, these are basically empirical equations which predict solar radiation availability in the form of monthly average daily global radiation. So, you basically average it over a month for the daily global radiation, and then monthly average daily diffuse radiation, and if you subtract monthly average daily diffuse radiation from monthly average daily global radiation, you will get direct radiation. Okay. Similarly, you can also calculate what is monthly average hourly global radiation and monthly average hourly diffuse radiation, and then daily or hourly diffuse radiation and hourly global beam or direct, you can say beam is often written as direct radiation, and diffuse radiation under cloudless sky. So, there are different ways of calculating this depending upon what you require, and this is what we will see in the next few slides. So, let us first look at monthly average daily global radiation, which is basically defined as Hg bar divided by H naught bar, that is equal to A plus B into S bar divided by S max. So, so you can probably cross that out, where Hg bar is monthly average of the daily global radiation on a horizontal surface at a given location. So, let us say if you are in certain location, for that particular location, this is in kilojoule per meter square per day. H naught bar is monthly average of extraterrestrial radiation on a horizontal surface at the same location, again in kilojoule per meter square day. S bar is monthly average of sunshine hours per day at a given location, so monthly average of sunshine hours, and S bar max is monthly average of maximum possible sunshine hours per day at a given location, that is the day length on a horizontal surface, and A and B are the fitting constants. So, these values of A and B have been determined by various authors, and for different locations in the world and in India, they are given here. So, range of S bar divided by S bar max and A, B values. Okay. Similarly, the value of A and B, they were determined by Modi and Sukhatme, and they were reported in 1979, and for different locations in India, they are given in this table. So, these tables are taken from again this book Solar Energy, chapter 3 by Sukhatme and Nayak. So, now let us look at the monthly average daily global radiation, that is the extraterrestrial radiation. So, this H naught is calculated by integrating the extraterrestrial flux over the day length. So, H naught is given as ISC, which is solar constant, multiplied by 1 plus 0.033 cos of 360 into n divided by 365, integrated over the whole day, that is, and you need to multiply cos theta, which is sin phi sin delta, plus cos phi cos delta cos omega, which is cos theta equation for a horizontal surface, into dt, and we know t is 180 divided by pi into omega in radians divided by 15, which can be converted into dt is equal to 180 divided by 15 pi into d omega, and then you can replace t with omega, so that you are able to integrate this equation from minus omega s to plus omega s, that is from sunrise to sunset. And by putting in the value of different angles and n, you can calculate what h naught value will be. Next, Klein further simplified this whole process for monthly average daily global radiation, and he said that for a particular day in the month, h naught is approximately equal to monthly mean value. So, you do not have to calculate for all the 30 days. For every month, one day will be sufficient. So, there are different, and they roughly fall in the middle of the month. You can see that the days are listed below: 17th Jan, 16th Feb, 16th March, 15th April, 15th May, 11th June, 17th July, 16th August, 15th September, 15th October, 14th November and 10th December. So, with the exception of June and December, pretty much all the values fall around 15th of every month. So, let us look at these through an example, which is example number 3.4 from Solar Energy book. Calculate the monthly average daily global radiation for a location in Baroda in the month of March. So, let us say for Baroda these values of A and B turn out to be 0.28 and B is equal to 0.48, and in the month of March, on March 16th, h naught is equal to h naught bar. So, March 16th turns out to be 75, and for that we can calculate what the value of delta is. Delta is minus 2.42 degree, which is the declination angle, and then we can work out what omega s is. Omega s is cos inverse minus of tan phi tan delta. So, phi is for Baroda we can take phi as 22 degrees and delta as minus 2.42 degree, and this will give us a omega value of minus 1.554 radians or 89.02 degrees. So, S max is nothing but 2 of omega s. So, we can calculate S max in hours by dividing it with 15. So, that turns out to be 11.87 hours, and S bar for Baroda is 9.5 hours, which is the average sunshine hours. So, we can also calculate these values of h naught by plugging in the values of different angles and number of day etc. in the h naught equation, and this value turns out to be 342.06 or 34,206 kilojoule per meter square per day. So, Hg bar is h naught into A plus B S bar divided by S max, and so Hg bar can be calculated as by plugging in the values in this equation, and this turns out to be 22,718 kilojoule per meter square per day. And these values are in fair agreement with the measured values, they are not very far from measured values. Similarly, we can do, so what we did earlier was this calculation of monthly average daily global radiation for a given location. Now, we look at monthly average daily diffuse radiation. Okay. So, global is sum of direct plus diffuse. Now, if we calculate diffuse and subtract it from global, we can get the direct value. Daily diffuse to global radiation ratio is related to daily global to extraterrestrial ratio by this equation. Again empirical equation, Hd bar divided by Hg bar is equal to 1.390 minus 4.027 into Hg bar divided by H naught plus 5.531 Hg bar by H naught square minus 3.108 Hg bar by H naught cube. The ratio of Hg bar by H naught bar is called as monthly average clearness index or KT bar. Here HD bar is monthly average of the daily diffuse radiation on a horizontal surface in kilojoule per meter square per day. And the data for India was modified by Modi and Sukhatme in 1979. There are a few more equations, I am just showing one of them. HD bar divided by HG bar is equal to 1.411 minus 1.696 into HG bar divided by H naught bar. So, this equation is valid for the range 0.3 to 0.7, and this should be bar should be here, not there, and this tends to agree a little bit with the data in the previous slide from Liu, and that is because the diffuse component in India is larger because of different reasons. So, let us have a look at a problem. Estimate the monthly average daily diffuse radiation on a horizontal surface in Baroda during March. Again 3.6 problem in solar energy book. So, using Indian data we can determine from monthly average global data. So, Hg bar and H naught bar can be determined using the previous problem that we have done, which is 22,718 kilojoule per meter square Hg bar, and H naught bar is 34,206 kilojoule per meter square. So, if we use the equation by Modi and Sukhatme and put in the value of A and B and Hg bar and Hg naught, we can calculate the value of HD bar as 6,465 kilojoule per meter square per day. So, you can now see that if this is your HD bar and Hg bar is this, so direct radiation will be Hg bar minus, so you can see this will be 22718 minus 6465 kilojoule per meter square per day, and this will be 16,253 kilojoule per meter square per day. That is the direct radiation that you get. So, you can see that ratio of direct to diffuse or diffuse to direct is 6. So, you can see that 6,400 nearly, and this is 16,000. So, it is quite large, it is nearly you can say 40% of the total value of the direct radiation actually. Next, we can calculate, we sometimes require not the daily data, but the hourly data. So, we can have monthly average hourly global radiation, and this equation is predicted first by Cloudless and Pereira in 1979. So, here we call it hourly radiation as Ig bar instead of H. So, H is for daily average, I is for hourly average or monthly average hourly value. So, Ig bar by Hg bar is equal to I naught bar by H naught bar into A plus B cos omega, and A and B values are given by these equations, which are a function of omega s, and Ig bar is monthly average of hourly global radiation on a horizontal surface in kilojoule per meter square hour. So, you can see it is not kilojoule per meter square day, it has become kilojoule per meter square hour, and you can't just divide it by, so in the day value you cannot just divide it by convert the day into hours, because it is only for 8 hours and it varies hour to hour. And I naught value, I naught bar is monthly average of hourly extraterrestrial radiation on a horizontal surface, again in kilojoule per meter square hour. So, there are different models to these, and so by Liu and Jordan, ID bar by HD bar is nothing but I naught bar by H naught bar, and Satyamurthy and Lahiri predicted this equation. So, there are different equations by different people, they are valid differently for different locations, and these are the expressions for A bar and B bar, which are valid between different ranges of HD bar and Hg bar, and they are again dependent upon the omega s values or hour angle values, and we can again have a look at these in terms of examples. So, calculate the monthly average hourly global and hourly diffuse radiation during April on a horizontal surface in New Delhi, the time between 9 to 10 hours, local apparent time, and average sunshine hours is 8.6 hours per day. Again, this is solved example in 3.7 in solar energy. So, daily data is April 15th is the monthly average day, that makes it n is equal to 1.105. From this we can calculate what is delta. Delta is 9.42 degrees. We can also determine what is omega s. It turns out to be 95.18 degree, which is 1.661 radians. S max is again twice of omega s divided by 15. So, this is 12.69 hours, and we can determine what H naught value is by plugging in different angles and value of N and ISC, and this turns out to be 37,034 kilojoule per meter square per day. And from these we can determine using the previous equations what the value of Hg bar and H naught bar, Hd bar were. So, this is similar to previous calculation that we did. Now, for April 15, 9 to 10 hours, I naught is nothing but ISC into 1.033 cos of 2 pi n by 365 into cos theta, and this makes it, so we do not have to, we just take it over an hour. So, this makes it 3738 kilojoule per meter square hour, and Ig bar by Hg bar is nothing but I naught bar by H naught bar into A plus B cos omega. So, we need to work out the value of cos omega A and B. So, we can work out the value of A and B by plugging in the value of omegas, and hence by getting the value of A and B and plugging in this equation, we can work out what the value of Ig bar is. So, Ig bar turns out to be 2389. So, Id bar using this will be Hd bar into I naught bar divided by H naught bar. So, Id bar turns out to be 789 kilojoule per meter square hour. So, this is for hourly value, okay, for every hour. You can do the same calculations using the relation of another author Satyamurthy and Lahiri, and this turns out to 780. So, the values are not very different, and it has been found that comparison between predicted and measured value, they show a deviation of about 10% up to 10%. So, it is a fairly good agreement. So, this is another way of calculating the radiation values. Third, we can have a look at hourly global beam and diffuse radiations under cloudless skies when there are no clouds, and this model was given by Ashray. So, here you have a solar beam which is coming on the surface with normal component being, with the direct component being IBN, and so we are interested in calculating the global radiation, which is IB plus ID, and IB is nothing but IBN into cos theta z. So, Ig will be equal to IBN cos theta z plus ID. ID is the diffuse radiation from the surroundings. So, it is a sum of direct radiation and diffuse radiation. And Ashray proposed that the value of IBN is A into exponential of minus B divided by cos theta z. Cos theta z is zenith angle, and ID is some constant C multiplied by IBN. And these values of A, B and C, they change during the time of the year and cleanliness of the atmosphere. And so, you can look at this table 3.5 in this book, but I have provided the values of few months. These are the values that you can take for different months. And if you do that, then for Nagpur, for example, for 20 June 1968, when declination is at the highest, we can calculate for a given times 9 to 10, 10 to 11, 11 to 12 and so on. You can see how the global radiation changes throughout the day. So, you can see that it is maximum between 12 to 13 hours, that is the noon time, and diffuse radiation is again 778 at that point, and direct radiation is highest in that period. So, for a given day, you can calculate the value of Ig and Id between different times for a certain set of values of A, B and C. Finally, most of the solar panels are not flat on a surface, they are on tilted surfaces, they are tilted with respect to horizontal. So, we need to calculate the solar radiation for a tilted surface. So, the total radiation will be the beam radiation, direct radiation plus diffuse radiation plus reflected part, or whatever the reflected part is from the ground, from the horizontal. Because the ground also reflects, so some of this get impinged on the surface. So, beam radiation we can calculate as the ratio of beam radiation that falls on a tilted surface compared to what falls on a horizontal surface, and this is called as tilt factor. So, we can say tilt factor RB is equal to IB at tilted surface divided by IB at horizontal surface. This is for beam or direct radiation. Okay. And for a tilted surface which is due south, the surface azimuthal angle is 0. So, gamma is equal to 0. So, we can modify cos theta will be sin delta into sin phi minus beta plus cos delta cos omega into cos phi minus beta. And for horizontal surface, theta will be zenith angle and beta will be equal to 0. So, this angle will be modified, because for a horizontal surface beta is equal to 0. So, you can modify this. So, this gives you the ratio between the tilted surface and the inclined surface. So, we can say RB is the angle, is nothing but ratio of cos theta divided by cos theta z, and these can be calculated using the parameters such as declination angle, the location and the tilt factor. And the diffuse radiation again is done in a similar manner. RD is equal to ID tilted divided by ID horizontal, but this is because diffuse radiation is coming from the ambient, and consider ambient as isotropic, that is sky is sort of isotropic, then there is a shift factor that needs to be considered. So, RD turns out to be 1 plus cos beta divided by 2. And the reflected radiation that comes from the ground, radiation shift factor for a tilted surface with respect to the ground, that is 1 minus cos beta divided by 2. And if you assume that there is isotropic reflection of direct and diffuse radiation that falls on the ground, so ground isotropically reduces all of these, then RR is taken as rho, that is reflectivity of the ground, multiplied by 1 minus cos beta divided by 2. So, the total flux on a given for a tilted surface will be the beam radiation multiplied by the beam factor plus diffuse radiation multiplied by the factor of diffuse radiation, that is RD. So, IB RB plus ID RD plus sum of beam and diffuse radiation that falls on the ground, which gets reflected onto the surface. Okay. So, basically it is like this, you have a panel like this. So, you have direct from the sun, then you have from the surrounding. So, this is your ID, this will be from the diffuse component, and then whatever coming from the ground, this is from the ground. Okay. This is your, you can say, the reflected part. Because it is no longer horizontal, it is inclined. So, there could be some component that would be coming from the ground. And this is valid for a surface with facing south. So, and generally most of the solar panels are facing south, because south is the direction in northern hemisphere where the sun is inclined, sun is shining from, and unless you track it, gamma is equal to 0. So, we can write this IT by IG as IB plus ID is IG. So, we can write this as IT by IG into 1 minus ID divided by IG plus RB, ID divided by IG into RD into R plus RR. And generally for a surface of concrete or glass, the diffuse reflectivity is about 0.2, and RR contribution turns out to be a very small contribution. So, most of the contribution is from the beam and diffuse radiation. So, we can ignore that. Similarly, we can calculate the monthly average, which can be approximated by calculation for the representative day. So, similar calculations can be made for the representative day by taking the average values. And the daily radiation on the tilted surface then can be, these are the daily values, instead of hourly values, these are hourly values IT, and these are daily values. So, daily values can be approximated in a similar fashion. HT divided by HG bar is equal to 1 minus HD divided by HG bar plus HD bar. So, this 1 minus H is nothing but, you can say, H direct bar divided by HG bar, right. So, similar equations, instead of I we have H, and these are the factors that you can, again you can have similar factors, the angular factors that can be calculated. So, for a tilted surface, again you can work out what the daily, hourly or daily radiation will be. And again the shape factor here, or the factor for the weighting factor for for beam radiation needs to consider this angular relationship. And here in this relation we will see that omega is on top and the bottom. So, the omega on the top is for tilted surface, whereas omega on the bottom for horizontal surface, because if you recall, the RB earlier was cos theta divided by cos theta z. So, this is for horizontal and this is for tilted. So, that is how these differences will be, and similar factors as were before, they will come for diffuse as well as reflected radiation. So, we can do a simple calculation, monthly average hourly radiation in Chennai with gamma is equal to 0 and beta is equal to 15 degree in October. So, we can calculate what is Ig, what is Id, what is rho. Rho is given, Ig, Id you can calculate using the previous examples. Solution, we can look at October 15 will give us n is equal to 288. On this day you can calculate what is the value of delta or declination angle. We can calculate what are the values of RB by putting in different values for the angles. So, we need delta, we need phi and we need beta and omega, and RB turns out to be 1.12. Similarly, RD and RR for diffuse and reflected radiation, we can see that RD is 0.983, but RR is very small, it is 0.0034. So, basically reflected radiation is very little, it does not contribute much, and whereas beam and direct diffuse radiation are approximately 1. So, you can then plug in the values of Id and Ig and you can calculate the value of radiation on tilted surface, which is approximately 2558, which is very similar to Ig. It is not very different. Ig was 2408 and we have got a difference of 150, you can say, kilojoule per meter square hour. So, by making this approximation. So, these are the way in which you calculate the radiations for different surfaces under different conditions for different, whether on daily basis or hourly basis, and these calculations are in fair agreement with the measured value. So, how do we measure the radiation? We measure the radiation by using two techniques. One is called as pyranometer and another is called as pyrheliometer. Both of these instruments basically convert the falling radiation into electrical signal, which is then converted into the value of radiation. So, this is your pyranometer, which is basically a disc under which you have some sort of sensor. So, basically it measures the total solar radiation by using a sensor. Sensor could be either a thermopile or photodiode, and it basically detects the heat or the electrical current that is generated when solar radiation is absorbed by the surface, and this signal is then converted into the intensity of solar radiation. So, this is pyranometer. Pyrheliometer, so this measures the total radiation. Pyrheliometer measures the direct solar radiation. So, it works along the similar principle, but instead of total radiation it measures the direct solar radiation. Okay. So, about these two equipment you can read a little bit from this books, Solar Energy by Sukhatme. I think this book talks about both of them, and there are a lot of other online sources about which can give you information about measurement of solar radiation using these instruments. So, in the end, to summarize the lecture, solar radiation is abundant. There is a lot of solar radiation that is present on the extraterrestrial surface, but by the time it comes to Earth, there is change in intensity because of atmospheric absorption and scattering. And it also changes as a function of wavelength, as a function of time, as a function of position of surface with respect to horizontal. So, we need to know about the geometry of sun with respect to Earth to exactly determine the solar radiation flux on a given point. and this can be worked out using variety of empirical relations as we saw in this class. And these values tend to be in fair agreement with the measurement which are conducted using devices such as pyranometer and pyrheliometer. This closes the discussion on solar radiation. In the next class, then now we will look at the materials that are used for fundamentals of the materials which are used for solar photovoltaic devices, that is the semiconductors. Thank you very much.